Good to see everyone. Welcome to our first proper machine learning lesson. And here we are. Now our first exercise is concerned with building a Meshgrid. So this is an NumPy exercise to prepare you for creating a coordinate grid, a coordinate system, a state space, whatever you want to call it, to prepare a coordinate grid where you can test the predictions of a trained machine learning model and see how it works in a very simple case. So we'll set it up in NumPy and we'll see a couple of functions that are important how to do this. And that's our first topic. See what we import. I've prepared the imports already. We use linspace, NumPy function to create grid coordinates, then Meshgrid to create the actual grid, and csub is a concatenate function that helps us to squeeze two things together into a single array. And then it's, of course, subplots in case we want to plot something. Right? Okay, so let's see how that works. And I'll start by doing a couple of definitions. In order to define a coordinate axis, points on a coordinate axis, we can use linspace. So linspace creates ascending numbers from a certain lower value to a certain upper value. So would you define those limits as a first thing, low and high? And I've chosen 1 and 10. Of course, you choose whatever you like. It's up to you. So low is 1 and high is 10. So we take numbers from 1 to 10. Then we need to define the resolution. How finely resolved do you want to have a certain grid? So you want a grid created then in X and Y. You have to define the resolution. So let's do the resolution. Number, so that's number of grid points per axis. Let's just put it 10, and that's what we need. So then we create the X vector, and the X vector will now be the grid points on the horizontal axis. So we use linspace, and we start from low, we go to high, and we take the number of grid points that we have defined. Quick, right? So from low to high, from 1 to 10, we want to have 10 numbers. So including 1 and 10, that's just 10 digits. And then I'm very lazy. I just copy and paste this. We'll just, for explanation, for simplicity, we'll just do the same thing twice. And it's, of course, not very elegant to do the same thing twice. It's not very elegant in programming. So I do a slightly better practice. I do this, I call the vector X equal to vector Y, and make them a sort of a copy. Okay, so now we have two vectors. One is called X and one Y, and we can print, we can see the shape because they are the same. We just need to see one of them. The shape of the X vector is now just 10, the 10 numbers that we, of course, have defined. And if you want to see what the numbers are, they are 1, 2, 3, and so on. So that's our, sort of defines our coordinate system, but now we need to actually create the grid. So having these two vectors, I go to my next, which is create grid. So my next session, now that we want to create a grid, we can use the concatenate. No, we don't use concatenate. We need to create the grid. So we need the grid X, and we need a grid Y. You will see in a minute why that is so. And to create a grid, we use Meshgrid. NumPy function imported above. I hope I have imported it, but we'll find out. And it's applied in a very straightforward way. You take the two vectors that you want to have to together create the grid and put them one after the other in that function. So if I execute the function, I have grid X and grid Y. And of course, you might now not immediately know what is grid X and grid Y. Let's just have a look. What is grid X? What is the result? So Meshgrid has created a matrix that goes, in this case, you can see you have 10 rows, which are all equal. Every row goes from 1 to 10, 1, 2, 3, 4, and so on. So let's have a look at grid Y instead. The same, a matrix, 10 by 10 matrix, but in this case, all the columns are the same. Now is column 1 is 1, 2, 3, 4, 5, column 2 is 1, 2, 3, 4, 5, and so on. So 10 by 10 grids arranged in just this flipped version. One has equal rows and one has equal columns, and these two together can now be used to create all possible coordinates on the grid that we want in the resolution that we have specified. It's actually fairly simple, but it needs an additional step that maybe is a little bit unusual the first time you see it, and that is you don't use for creating the actual coordinates as pairs, like, coordinate is like give the X coordinate and the Y coordinate, and then you know where a certain point needs to be. So we can do that. It's called the Cartesian product, but we need to flatten the grids to do so. So how do we flatten the grids? We create grid X flat. So flatten is a technical term that's often used in machine learning. And it just means you take the grid that we have, the matrix that we have just defined above, and you put it all in one long array without rows and columns, just one long array with 10 by 10, in this case, 100 numbers. So that's called flatten or linearization sometimes. And this is very easy. If you have the matrix, one was called grid X, you can do that with the function or method revel. So if you, without any arguments, apply revel to that grid X that we have created, then you can create grid X flat, which is then, if I scroll up, and then make it slightly more bigger so you can see that a little bit better here. And so that grid X flat is now nothing but the sequence of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as we had it before, but instead of starting a new row, it just continues 1, 2, 3, 4, 5, and so on, until the last number is, of course, a 10, because 10 times 10. And so we have 100 numbers. Can check by asking the shape of that. It's 100 comma nothing. It's just one long array with 100 numbers. And as you might guess, we do so the same for the Y grid and create a linear version of the Y grid. And if we look at the Y grid flattened, then it's 10 ones, followed by 10 twos, followed by 10 threes, and so on, down to the last 10, the last of 10 tens. And so we have now two flat arrays, 100 elements each. They can now be aligned in order to create the pairs of coordinates for each of the points in the grid in two-dimensional space, horizontally and vertically. So we want to combine it if we want to have that, Cartesian, that's actually, no, I'm going to do that. Conversion to Cartesian product, that means create the combined grid. And this is fairly easy to do. So we call that my XY space or XY grid or whatever, space, whatever you want to call that. And we use the concatenation function C sub. So C sub is a lowercase c with a sub under it. It's a bit of an unusual number in that it takes arguments in square brackets. This is very exceptional, right? It's only here. Most other functions don't do that, but here we have to do that. And we just say what we want to have concatenated or joined together. And we have grid X flattened and grid Y flattened. So those long one-dimensional arrays. and we use that to produce our grid space. Right, so I have immediately put XY space below it so we can see the output and you can see what happened. So the first point of coordinates is 1, 1. That's our lower left corner. You can already guess what the last one will be. Second point is 2, 1, 3, 1, 4, 1, and so on. Then the next goes after 10, 1, we continue 1, 2, 2, 2, 2, 3, 4, 3, and so on. And all the way down 100 pairs. The last one is, of course, 10, 10. Right? So this is the Cartesian product. This is our coordinate system. And this means you have in one array, XY space called here, you can just sort of open up that whole space. And as you remember, upper and lower limit were defined by us and don't need to be the same in X and Y. Can whatever limits you can choose, borders you can choose yourself, and the resolution defined in this case by our variable, which is called number. The same, you can do whatever resolution you want in each X and Y, can be different if you like. So now I have told you it's a grid. Do you want to actually see the grid? Yes. So let's do it. Let's just plot the grid so we can see it for once, then we are finished. See what it looks like. So we create our plot, which is subplots. We create our coordinate system. And then we scatter the grid points, and the grid points are included in our XY matrix, XY space. Is it called XY space? I think it was called XY space. And what do we do on the horizontal axis? We want to have all, it's not quite right, we want to have all the rows of the first column, which is index 0, comma, and on the other axis, we want to have all rows of column number 1. So first column versus the second column, that's horizontal axis versus a vertical axis. And if we do that, maybe put a semicolon at the end so we don't see this comment here, then this code produces our grid. Finished, all said and done. And I leave it for you to have a look at, where is that? To have a look at the tutorial in our NumPy tutorial, NumPy array tutorial. You can see that this grid, that it takes very little extra coding to do all sorts of nonsense like I did here, but this is just for practicing with it, matplotlib functions at the same time. So here's your grid. X coordinates, in this case, integers, doesn't have to be integers. You can use any real number. Doesn't have to be positive, can go from positive to negative or the other way around. Whatever you please, it will be fine if you follow this convention. So now the use, why are we using this? We are using this when we do in the lesson. If you have done the lesson, of course, some even have uploaded the assignment. So if you have looked at the lesson, we are using this to create a space where we test the predictions of a machine learning model. Right? Once you have trained a machine learning model, you are able to predict, and then you can define the space into which you want to do your predictions, and you can see the predictions in a space, and you define that space by creating a grid. So that's why it's very useful to sort of have that, then just open it, test it, and of course it's a bit limited. You have only X and Y. We can't easily visualize 10-dimensional grids, although NumPy is able to easily handle it for you and create 10-dimensional grids if you like. Good. Next. So that was this. Let's do another NumPy array exercise for preparing us into the actual machine learning system. And this is another topic, is often underappreciated. It's very important. And we have briefly touched on it in the data handling session. So I'll just bring it back to you to show you why that is so important. What we want to do is we want to see how to create arbitrarily defined sets of data. And one way of doing that is create random numbers. And why we do that? We want to be able to create arbitrarily large test data sets on which we can test any algorithm or statistics or analysis method before we see that we trust what we have obtained from our actual data. So we compare data against sort of surrogates or substitute data. And for this, we need to know how to reasonably and effectively create those data. So one way is normally distributed random numbers. Probably you know normal distributions like the Gaussian bell curve. That's typically you assume there exists in your data a mean and it has a certain distribution width. And so you can maybe say probably they are normally defined, and then a lot of statistical things follow. We do it without any assumptions about the data, but normal is one of the standard ways of starting to think about data, normal distribution. So we just use it. The aforementioned tutorial on the website, on the Moodle, has the same done with uniformly distributed random numbers. So that's another way. Okay, so let's see what we need for this. We need to import something. What we need to import in this case is normal. Function normal, NumPy function to create normally distributed random numbers. And we'll at the same time have a look at how to use the seed function, seed, that helps you to have randomly created numbers, but a way of controlling that you actually control the randomness, so to be able to actually reproduce if somebody has done it, so you can reproduce what they have done to the numeric value that they also have. So we do that by using the seed function, and let's prepare this. We need a constant. So we call that random seed. You will see that professional programmers tend to do constant parameters with capital letters. Not typically following this convention, but it's a way of a number that is sort of defined at the top of the script, and which is then true for the rest of the script. So in this case, you could use this random seed. It's just an arbitrary set of digits, 1, 2, 3, 4. You could use that throughout the script, even whatever its length, and then make it reproducible for others. So we use that to seed. Our random number generator means we prepare the creator of random numbers such that the same sequence will follow every time I call it. And then comes our random number generator. So here's something that is very important in machine learning, to learn samples and features. So we define samples and features, and that is in a matrix like the one that we did before in our grid, in our coordinate grid. Samples refers to the number of rows, and features refers to the number of columns. Rows, columns in that order. And we just say how many do we want? 10 rows, 2 columns, just an example. Right? So we have 2 numbers assigned. And then for a random distribution, you have to look it up. It's a bell-shaped curve, and it has a center. We need to define where that center is located, often called the mean, and then the width of the bell, and that is the standard deviation, or STD. So if we define those two, like in all textbooks, you will find 0,1, so mean 0, centered at 0, and standard deviation 1, yeah, certain width. That is easy to calculate. That makes the formula of the mathematical formula of the function very easy. Put in whatever number you like. Just you know that it's the mean and the standard deviation. And then we create random numbers. A variable called random numbers. And we apply our function, which is called normal, and then follow the convention to set up our array according to the definition of the normal function. It's not yet being called, so Just first execute this here and now. So the order in which we provide the arguments is the mean comes under log or location, and this where we provide the mean. Next thing, a bit unusual, it's called scale. You have to remember that's the standard deviation, so I like to call it STD. And that's in that order, mean, standard deviation, comma, and then the size of the matrix that you want to create. So we know it already. A keyword, if you like, is size, and the size, so two-dimensional matrix needs to be provided as a tuple, an array with 2 dimensions. So can you even see that? I'll go a little bit up. Now you know what it is. So, and the size, of course, we have defined, what did we call that? Samples and features, rows, comma, columns. So the size is samples, comma, features in brackets to make it a tuple. And then, of course, we'll create a matrix of random numbers, 2-dimensional array with rows, as many as we have specified in samples, columns as many have in features. And as the earlier you get used to samples and features, the better it is for reading any text on machine learning, especially the more it comes from the computer science side, the more this will be the way to talk about it. And if you want to see it at the same time, we can format it a little bit more nicely, and that's maybe more readable for you at home. So mean, standard deviation, sample size, and then let's just check what happens. Random numbers shape, called the shape. So we've created the array. It's a 10 by 2 matrix. It has 10 rows and 2 columns. And let's just have a look at it. This is what it looks like. So we have done it. And we have forgotten one thing. Namely, we have forgot to use what I said in the beginning. We have not seeded our random number generator such that it produces the same type sort of random numbers every time I do it. So if I go back to my code and execute it again, watch the first line of numbers. First is 1.4 minus 0.5. Now I execute it again. And you see, now every time I call this function, it creates different random numbers, right? So of course, then however many times I use it, I will not be able to reproduce anything. If we want that reproducible, we can do so by calling the seed function before we do the call of the random number generator. And seed, we can just seed. We can offer the argument random seed, so we have a specified number, and that will reset the random number generator. If we now execute it, can I maybe, it's a bit too many, let's round that to 2 digits, say. Yeah, that's better, right? So I have seeded the random number generator, and you can see the outcome, 0.47 minus 1.19 in the first row. Do it again. And this time it repeats. Why? Because the code executes it after setting the seed function, so it's reset. So this time, I'm sure every time I rerun the code, I will have the exact same random number sequence. So that's good. I like it, but it's of course something special. If you share code, then somebody else will be able to reproduce the same set of data. Right, so let's close this up. This is how you do it. And let's close this section by having a look at the plot distribution. So last topic is here, well, the usual fig ax. Right now you know this convention already. Sub. Have I not executed that? Or I have not imported it, so I need to import that from numpy dot from matplotlib import subplots. And then subplots, I can open my axis and I can draw a histogram. And what I want to do is I want to do the histogram on the random numbers that I've just created. What were they called? Random subnumbers, so it's correct. And number of bins, well, I don't know. I have in my text, it says 30, it doesn't matter, it's just something. And of course, all this nonsense that we don't want to see. Here is my histogram. It's a poor histogram. Why is that? Well, because I've only created just a couple of numbers. Let me just go back and instead of 100 samples, let's get 1,000 samples and rerun the code. And then we have a plot distribution that's a bit nicer. Now we can see actually the Gaussian distribution behind it, the bell-shaped curve already coming to produce that shape. And yeah, increase the number of bins a little bit. It's too much. Yeah, 30 was actually good. So we used the number that's in the script. So we can see two distributions by default, one for each column. So we have two columns. So we have orange and blue. Well, the first is actually the blue matplotlib, and we can see the distribution of the data, and they work as expected. So yeah, that's it. You can create any number of rows, any number of columns that you want to handle. So if you had like a data set that you want to reproduce, you can say you have 150 samples with 10 columns, then you create 150 samples with 10 columns, but instead of creating one, you don't use the same random number generator, but you use different seeds, and then you can create different realizations of the same distribution as your data. So you check the mean value of your data, put it in as mean here, then you have equivalent random numbers, and you can test, for example, whether your data are normally distributed. Talking about this, just one thing that's actually nice, namely, now thinking of it, right, that I say, well, if you test your data, then of course not every column, not every feature in your data will have the same mean and standard deviation. It will be different. And of course, you are able to do that as well. So if I just copy that code that I used to create the random numbers, if I copy that down here, so this is the generator of random numbers, and I have the mean and standard deviations. Of course, I have given one mean and one standard deviation sort of for all. But if you look up the documentation for that, that's Shift tab on your keyboard will bring up the documentation, and scroll down, and then at some point it says log and mean value and scale the standard deviation. It says log can be a floating point number like we did, we said 0, or it can be array-like. And the same for scale, the standard deviation can be float or array-like. Means array can produce, you can offer many numbers as arguments. So let's try one. Let's try an example. If we have two features, let's produce a tuple. Let's offer a tuple, two numbers, offer them as a tuple, and something like 0, 10. So it means we have a first mean that is 0 and a second mean that is 10. And similarly, it's a standard deviation. Instead of offering one standard deviation, we offer two, like standard deviation 2, standard deviation 1, just two numbers. So it means we have one value for the first feature, one for the second feature. And I just copy and paste this code here to plot it. If we then do this, so I also call it random number, so I can also get the histogram of this thing here. There's something wrong here. It's obviously there is a parentheses missing. So I have one too many here. I think that solves it already. So you have created tuples, but with one parenthesis too many. And if I actually correct this and make it nicely, then we get a nice visual display of the histograms. And in this case, because I have taken two values for each, the mean and the standard deviation, we get now two different distributions. So it means, yes, with this little trick, you can actually have a distribution like any of the features that you have in your own data set. You can produce as many distributions as you like with features as specified by your data. So it's extremely convenient. So it just put in two numbers and it creates it like this. And here we have this zero distribution or zero center distribution here with the broader standard deviation and the more narrow distribution around 10 in orange on the right-hand side. Okay. If you don't feel comfortable doing this or coding this yourself, please go back, use that tutorial to practice. As I said, the more you practice this, the more you can concentrate on the actual machine learning features and not be worried about those sort of more trivial basic skills, so to set up things and know the arrays and where's a tuple and where's square brackets, round brackets, and so on. Right. Did I forget anything? What's the use? Yes, I said what it's used for, and that concludes our second topic for today. Right. So, well, I think we can get then ready to have a look at our third topic. And for our third topic, I will do a slightly different way. Now, so far I have sort of typed in the code for you, with you, sort of as I talked, typed it along. In that last part, I will now take the liberty to actually copy and paste code that I've pre-prepared. You remember where to find that code, right? You can download it from the Moodle. I will use that exact code and maybe only make small modifications. So if you want to follow, you should be able to, and we'll discover if there was an error there, then it will show up, then we correct it here. But it just makes things quicker and makes me a little bit more focused on the actual concept as I go through the basic workflow of training a machine learning model, and in this case, introduce classification. So we do that. How do we do that? So I'll comment on the code in any case. Hopefully you can see that. I did it a little bit smaller. It's not big enough. So I want you to see everything. First part, we create training data. So maybe I'll just go quickly through it. For classification, what we want to do. So we want to see some data. First, we want to see some data that have been assigned labels, so that have been categorized, that have been divided into, say, diseased, healthy, control, right? Two categories, and it's either this or that, period. What did we have in the lesson? Is smoker, non-smoker. Somebody asked the person and wrote down, according to what the person said, this is a non-smoker, so non-smoker, or this is a smoker, smoker. So we have a categorization here, or any other that you can come up with. It can be green fluorescent labeled yes or no, labeled, non-labeled, and then you put in a category at the end of your data frame and you say, which one is it? Male, female, big, small, good, bad, whatever you like. And this labeled data set will be used to train a model. Sort of the model takes the data set, doesn't look at the labels, makes a prediction and then checks versus the labels and tries to then self-improve. So in an iterative process, so it finds, well, obviously, if you have never seen the data before, you predict something at random, it will mostly be wrong, and sometimes maybe accidentally right, 50% right, 50% wrong if it's two labels. And so you're not doing very well, but what you can do, you can improve the model, you can try to change the model slightly and then see, is the prediction getting better or worse? If it gets better, you continue in that direction, improve more. If it gets worse, you reverse and go in the other direction. So I think that's the basic idea how a machine learning training works. You do some prediction and then checking what labels were provided. You see whether you are better or worse, and such that you can, under the guidance of those labels, that's supervision, you can try to improve the model until you reach a point where you can't improve the predictions anymore. And because we need that, so we need to have labeled data. And once we have labeled data, we can do this training, get our best model. And when we have the model, then we want to, for the future, be able to predict whenever you give me similar data, so data of the type that I've used for training, then I can take those data, I can sort of run them through my internal model, my optimized model, and I give you back the prediction, and I tell you, oh, these numbers are certainly from a smoker or non-smoker. I just tell you what I think it is based on the previous experience with the labels that you provided. So this kind of prediction is at the heart of everything machine learning, right? That you sort of train a model, a generic internal that we're not doing mathematically here, just use it sort of as a black box. And you come up with an optimized form that helps you to just input data and get the category or some prediction, whatever you like. You can predict anything you want. Have that as an automated output such that you can then no longer need to worry about it. You just get the data and you know what it's supposed to be with a certain confidence. We'll talk about this later. So that's classification or supervised machine learning. Many more things. Look in the materials that I don't tell you now. We want to have now a run through the classification workflow. So setting up test data. You can already see the code, it's random numbers. And then we do a classification training, provided, given some labels, we do a training, then we do the prediction. We do categorical prediction, probabilistic prediction, and then we check, what do we do? Then we check the feature importance. We check how this prediction takes each of the columns in our data set into account. And finally, we sort of end then by asking what else do we need to do in order to get the best possible outcome. So did you understand that? So it's here on the left-hand side, train the model, create test data, predict labels, predict probabilities, and get the feature importances. And I will explain what each of this means as we go along. So this code here is very simple. It just takes what we did exactly as we used it now. Take a random seed and then create data from a normal distribution. So it doesn't work. Why? Because seed is not defined. So where is seed? We haven't imported anything, so I need to activate my functions. Let's see, seed is there. Okay, so now I have activated it. It should now run. So seed is defined, random seed is set, seed is called, random numbers are created, and we have, as a result, we have training data, which are called capital X. So the random numbers from previous, I have now relabeled, I've given them the name X, capital X, and I have created training labels. And now we have to take a look at how did I do that? I took a function called zeros. It's a NumPy function that will create an array that is all zeros. And when I say samples, you remember samples is the number of rows. It means we have as many zeros as we have numbers of rows. Why would that be interesting? Well, it's not, but we can make it a little bit better for classification in that we set the second half of the numbers arbitrarily equal to 1. So that is done here. So from half of the sample size to the end, we put everything equal to 1. And then we have a one-dimensional array with 50. How many do I have? 100 data, so 100 rows. So 50 of them will be zeros, another 50 will be 1. And these are labels, right? Remember the categorization, smoker, non-smoker. Here we have zeros and ones. And they are of a size that is actually nicely aligned. Our X array, capital X, is 100, 2, 100 rows, 2 features, exactly as we had defined it before. In this case, random numbers, but you substitute that with data if you like. Y array, that lowercase y, is our labels, set of labels that we have. And we have 100 labels, and we say first 50 numbers are category 0, just invented something, and the second are category 1, some category. So what's important to remember here is this convention, capital X, lowercase y. That's how we do it in machine learning, and all of the tutorials in Scikit-learn that we're going to use are using this convention, capital X, for the data, training data or data that you have, lowercase y for the labels. And of course, you can extract that and put it there if you have that somewhere in your data frame, as we had it in the data handling sessions. So I created those two things, capital X and lowercase y. And let's just have a look at those. Let's just see what they look like and make, no, that's not the right thing. I wanted to have a code to plot this. Make a scatter plot. These are our 100 data points. So they are sort of scattered somewhere around, and whatever then mean, and you have to look it up, whatever mean I chose. I don't want to bother how I defined the normal distribution. Somehow I came up with this set of numbers. A nice trick that we can use here is, of course, now that we have the labels, remember we have zeros and y's in the lowercase y array, we can actually use them to see which of the data points belongs to one, which of the data point belongs to the other category. And we do that by saying C equal Y. C is color, and Y means you will have either 0 or 1, right? There's nothing else. And because matplotlib auto scales, you will be on one extreme of your color scale or on the other extreme of your color scale. And if we use our already used color map, which was the blue, white, and red. So we have blue on the lower end and red on the other end. And we introduce that now we have the labeled data. And you can see the blue label is all those labeled 0. So blue point means this is one of those categorized as 0, according to how we set it up. And the red ones are category 1. Easy, right? So you can use this kind of code and see your data immediately, and you will see, well, for classification, this is an extremely hard or almost impossible problem. Why? Because how do you want to decide whether your data are from one distribution, the red one, or another distribution, the blue one? We don't care. We just say, well, that's the machine learning's problem, and we'll have to do that and see what comes out of it. So let's do that. Let's take the code, and this is code from the textbook. So I will just copy and paste it here to tell you how we do it from sklearn, so from Scikit-learn. Yes, that's our library from now on. We import a classifier, which is the random forest classifier. It's also my t-shirt. And the random forest classifier is one of many good classifiers. It's a good one to start with, so that's why we're using it to introduce you. you will see everything that you need to see with this one. And next session in 2 weeks, we'll have 7 or 8 more classifiers that you can look at. So we import this random forest classifier, and we have it, and we use the random seed as before to make sure that everything is reproducible, the call of the seed function. And then a peculiarity about this is that the random forest classifier is a class in Python that needs to be instantiated. So instantiation means you just prepare it sort of in a naive way. Random forest classifier, you call it, you say, take this random number generator with a certain seed, and then you get something called CLF. And CLF is nothing but a prepared, naive, untrained model, internal, hidden, we don't really see it, that is waiting to be trained. Okay, so you check in the material, it says a little bit more about how this works. And here for brevity, just how do we do the training then? Well, the training consists in calling a function or method called fit on that classifier. The naive classifier CLF.fit means train that classifier using data X, and in the supervised machine learning with labeled data using labels Y. And you remember why these labels are meant to help check whether a prediction is correct or no. And if we execute this code, nothing happens. And that's all the machine learning done, and we are finished. Well, almost. We haven't really seen anything, but you can see the random forest classifier sort of returned as a trained classifier, now started from seed 111 in this case. Our work is now to extract the results of this random number classifier and to work with it. So what we do is we actually go and create test data. So now we pretend this is all done, and now we pretend new data have come in, right? So we need to create something, and yeah, we don't do anything new now. Same thing as before. We use 1,000 test samples, now testing whether the algorithm actually works good. We create numbers from the normal function using random numbers, but we use a different mean and a different standard deviation, so a different distribution, but we just get 1,000 random numbers. But observe, I don't want this second line here, observe that if I just do it like we did before, more nicely formatted, test samples and features, we're now at the same number of features as before. So I haven't changed features, features still 2. And this is a must. You can't do test data that have a different number of features from the number that you used for training. If I use 1 or 3 or 10,000 features, it will not work, will complain, because we have trained it on 2 columns or 2 features. Samples is up to me. I can have as many new data as I want. So I create 1,000 here. Yeah, it doesn't matter. You pick the number. So let's see if it works. And we call that capital X subtest. And it has 1,000 rows and 2 columns, as you can see here. And why are we using new data? Well, now see, how can we see what the model actually predicts? So we do model prediction. Model prediction is predict the labels. Now CLF, we use our classifier. This is the trained classifier from random forest algorithm. And we say PR, what does it give us? Predict, right? One of the things that we can do with the classifier, we can use it to predict. And as an argument, of course, we provide the data that we've just generated that don't have any labels or anything. Just do that. Oh, look at this. When we execute the prediction, we get in return labels. Actually 1,000, if we have created 1,000 rows for the test data, 1,000 test data, now we get 1,000 labels. And this is what the machine learning model, the trained machine learning model, thinks the data are. And this is row by row. So we get 1,000 predictions. First is 1, category 1, second is 0, category 0, 1, 1, 0, 0, and so on. Of course, this is now random, right? We have used random numbers, so there isn't much structure in the data. So it's maybe not as meaningful as you would think it is, but nevertheless, you can assign this a value, y predict, and then you say y predict shape. And of course, by this, you get as many rows as you have test data provided. So test data was 1,000 rows with 2 columns, and so you get 1,000 predictions. And yeah, predictions you can then check. Is it good or is it bad? Of course, here makes no sense because it's random. Let's have a look at something a little bit more specific, namely predict labels. We have done the predict probabilities. So the second thing you can do is you can actually call that same trained model. And you can see there's 2 more things that we can do. We can not only predict, we can also predict probabilities. So let's do this. Let's predict probabilities on the same array of test data. And now you will get 2 numbers, which are the probabilities of each of those predictions that were made previously. Right? So if you remember previously, the predictions, y predictions, say the first 10 predictions were 1, 0, 1, 1, and so on. And now, if we say we do the prediction probabilities, say the first 10 only, then what you get is the probability of that label that we had up there. Now, the probability with which the machine learning model thinks this is actually correct. So it's very sure about the first prediction. It's 91% category 9. But it's absolutely not sure about the second prediction, which was 0. So if we go back, it was a 0, but it's about 50-50, right? So that's about a coin toss and so on. So it gives you the probability internally estimated. How sure am I, given the training data, that this prediction is actually correct? So extremely useful because you can see not only get a prediction, but you can also see whether the model hesitates or is confident in you taking over that prediction. So we're nearly finished. We want to see one final feature of those classifiers, which is extremely important, and that's this feature importances. We had 2 features, and they were both used in order to train the model to predict. Now, we can also get from that trained classifier under F, feature importances, right? This feature importances, this instance here. And if we don't need to provide any argument, if we just take it like this, well, it gives us 2 numbers. 2 numbers, what? We have as many numbers as there were features in our data set. So we had 2 features, 2 columns. So we get 2 numbers. If you have 10 features, you get 10 numbers, and tells you to what degree did each of those columns contribute to the prediction made above in discrete or probabilistic fashion, right? So what it says here, 51, 48, if you look at it, percent is both features contribute about equally to the prediction, which is not a surprise because, of course, it was from random numbers. Why would there be any difference? But it might be if you have 100 features. So if you have proteomics data, 100 different proteins, then you can see which of those proteins is most responsible for the predictions made, say, of a certain phenotype that goes ahead with the sample from which you made the proteomics analysis. So feature importance is an extremely nice way of looking at how did those columns that are provided actually contribute to the success of prediction, meaning if you have 100 proteins measured, 100 features, And most of them don't contribute, but few contribute a lot to the prediction. Maybe in the future you don't need all the measurements. You can actually reduce it and concentrate on the important predictors in order to train your model. Okay, final thing. Let's stop this lesson. Our first workflow go through with having a plot. And I have the code here for a plot that is very similar to what we did, a scatter plot, but now instead of the training data, now of the test data. Remember the test data that we created? So we called them X-test. So I scatter the test data. If I take this away, these were the test data that I created. And what I wanted is now use the coloring of the predicted labels. So the labels that the machine learning model gave me. So I used that as a color to see how did the machine learning model actually think to divide that space into red and blue in this case, or 0 and 1 labels. And here you have the outcome. So the machine learning model in this case tended to have those on the horizontal axis that are on the left-hand side to put them as red, and on the right-hand side as blue. And then you sort of, this is your grid, if you like, where you can use also Meshgrid to test it on. But here you can see how the model thought these data had to be divided in order to come up with a good prediction. And you might notice that a lot of the red dots are somehow hidden behind the blue dots. So of course, there's a lot of confusion and a lot of predictions that are around 50%, so not so very sure. That's it. That's how we are at the end of our first get to know my random forest. And you saw a little bit how set up data, train the model, and then get some important features out of it. And with this jingle in the background, kindly provided by Adam Lee, who is in the audience. Thank you, Adam. And thank you to those who have already uploaded their assignment. And I'll see you in 2 weeks when we have a much deeper revision of this and we look at more features, how to improve the prediction in case it's not so good the first time round. And otherwise, good coding. Bye.